Hello, students. So this video here is about Polygon congruence, and since we're specifically talking about triangles, again we'll work it going into triangles. But again, this video here in this lesson is about Polygon congruence. All right, so guys, we've discussed congruence a little bit, sort of, kind of, in previous lessons, but again, folks, now we're going to kind of go into it a little bit deeper, and we're going to kind of remind you of some of the things that we have discussed congruence with as well. But anyway, let's go ahead on and get started here. All right, so folks, here we go. This is just the basic concept of what congruency is. Two geometric figures are congruent only if they have the same or equal measures. So guys, we've talked some about congruency before, and when we did, we've mentioned that when we say the word congruent, we mean that we're talking about that those geometric figures have the same or equal measures. All right. So again, so guys, we could be talking about a simple geometric figure like a line segment, like two line segments being congruent. So if two line segments are congruent, that means that those two line segments have equal measures. We could be talking about a simple geometric figure like an angle, so two angles are considered congruent angles if they have the same measure, right? Or we could be talking about more complex type of geometric figures like polygons, okay? So two polygons are congruent, and we'll get there. You thought I was going to say it right there. But for real though, two polygons are congruent if they have the same measures. But of course, we'll give that a formal definition just in a little bit. All right, so guys, let us kind of take a little walk down memory lane. Yeah, a little walk down memory lane. Whoop! Now wait a minute now. If that's what memory lane looks like, I don't know if I want to walk down that one. But yeah, nah, just joking, guys. But no, for real, let's take a little walk down memory lane. Seriously. So guys, we've talked some about transformations, right? And we've done previous lessons on transformations. And when we talked about transformations, we mentioned that some of your basic types of transformations are isometries, or in other words, are called rigid motions, right? And so let's kind of look at and remember our discussions about that. Okay, so folks, on this little walk down memory lane, let me ask you this: do you remember this right here? Out of those four basic geometric transformations, and again, those four basic geometric transformations that we had discussed were translations, rotations, reflections, and dilations. Out of those four basic geometric transformations, there was only one type out of those four that does not produce congruent figures. Do y'all remember which of those four basic geometric transformations does not produce congruent figures? Do you? You remember which one of those four basic geometric transformations is not an isometry? Which one of them is not a rigid motion? Which one does not produce congruent figures? Well, let us remind you if you don't remember. All right, so I'm going to ask y'all again. Do y'all remember this? Because again, we talked about this. And again, we said that a dilation is not an isometry. A dilation is not a rigid motion like the other ones out of those four basic geometric transformations. And again, we defined what an isometry was in that previous lesson that we had done on transformations, introduction to transformations anyway. And we said that again, an isometry or rigid motion is a transformation that preserves both the shape, which means that it preserves the angle measurements, and an isometry preserves the size, which means that it preserves your side lengths, right? And so we defined what an isometry was, and we said that with an isometry or with a rigid motion, where we at? Yeah. With a rigid motion, the pre-image and the image will be congruent figures. So whenever you got a transformation that is an isometry or a rigid motion, so whenever you've got a translation, and you should remember what a translation is. When you slide a figure left, right, up, or down, and the orientation of it doesn't change, but it's still it still looks like it's oriented the same way, but it's just been slid or dragged left, right, up, or down. All right, so when it's a translation, a rotation, or a reflection, right, those three are isometries or rigid motions. And with those three types of transformations, your pre-image and your image will end up being congruent figures. Whether we're talking about line segments or angles, or whether or not we're talking about polygons, which this video happens to be talking about congruent polygons. But anyway, so again, only isometries or only rigid motions can produce congruent figures. And again, in that little previous lesson that we did, we had discussed that a dilation, and we know that dilation is a type of transformation that either stretches or shrinks your geometric figure. A dilation only preserves the shape, which means that it only preserves the angle measurements. But again, a dilation does not preserve the size of whatever the geometric figure is, meaning that it does not preserve your side lengths. And so usually, guys, when we're discussing congruence, not that it has to be, but usually is referring to those more complex geometric figures like polygons. And so again, folks, a dilation can only produce similar figures. And folks, we'll talk some about similar figures after we get finished doing all of our discussions about congruence and triangle congruence. But anyway, folks, that's our little walk down memory lane where we have discussed congruence before, and that was the first place, if I'm not mistaken, in this class that we discussed congruence when we were talking about transformations. But again, that's if I'm not mistaken, that was the first place where we discussed congruence. In this class, I'm talking to my students enrolled in my classes at our school, you know. But anyway, let's look a little bit more at congruence. All right. So we're getting off of our memory lane now, and we're getting back on the main highway, talking about congruence. All right. Okay. All right. So folks, again, we're not walking down memory lane anymore. So again, folks, remember, two geometric figures are congruent only if they have the same or equal measures. Guys, a congruent polygon. Congruent polygons have congruent corresponding parts. In other words, when we say corresponding parts, what we mean is they're matching sides and angles. So again, congruent polygons have congruent corresponding parts. All right, and then, guys, a congruent statement. A congruent statement is of course a statement that expresses that two or more geometric figures are congruent. Usually, guys, usually the congruent statement will be using algebraic symbols, and it won't just be like a verbal type of expression. Usually, it'll be using algebraic expressions. But again, a congruent statement is it expresses that two or more geometric figures are congruent, usually using algebraic symbols. All right. So, folks, you see this diagram that I have over here on the right, where you see these two polygons, these two four-sided polygons. Each one has four sides. Each one has four angles. Technically, they're quadrilaterals. But anyway, that's the type of polygon, four-sided, four angles, right? When you name congruent polygons, or whenever you write out any type of congruent statement between their corresponding parts, if you're going to do that, and if you're going to state, if you're going to write out some type of congruent statement expressing that two polygons are congruent, or expressing that their corresponding parts are congruent, then folks, when you do that and you write out that congruent statement, listen, when you write out a congruent statement, naming congruent polygons or writing any congruent statement between their corresponding parts, you must list the corresponding vertices. Vertices is plural for vertex. You've got to list the corresponding vertices, the corresponding corner points in the same order. You've got to list. And let me explain what I mean, folks. If you're not getting it by what I'm saying, that's why I'm explaining it right here, right now, so that you can get what I mean. Okay? So, folks, you see how over here they've got these corresponding angles listed out, and those are the corresponding vertices, the corresponding corner points. They're saying that point P is a corresponding vertex with point G, and you know that they're matching because you see congruency marks, matching congruency marks for the angle P and the angle G. Yeah, you see that. So again, folks, so they've got these congruent statements here between the angles, between those corresponding angles, and they've got congruent statements also between the corresponding sides. Now, folks, again, so let me just show you real quick what we mean. For instance, right? So we know that angle P corresponds with angle G, right? And angle Q corresponds with angle F. So again, P is congruent to G. Okay, y'all see that, right? P goes with G and Q goes with F, right? Y'all see that? P is congruent to G, Q is congruent to F. Okay, y'all see it. Y'all see it. Anyway, so notice the way that they wrote out this first congruent statement with the sides. They said that the side PQ was congruent to. Notice how they didn't say side PQ was congruent to side QF. I mean, they didn't say it was congruent to side F. Sorry, they didn't say it was congruent to side FG, because this would not be correct. Okay, not correct. Why is this right here not correct? Because P is not corresponding with angle F. The vertex that is corresponding with angle F, the vertex that's corresponding with angle P is angle G. You get what I'm saying? P corresponds with angle G, not with F. So what I'm saying is that they have to be in the same order. If you're going to write out a congruent statement, it has to be in the same order, where those matching or corresponding parts are written with the same order. I'm trying to emphasize this so that you know, okay? So what I've just written would not be correct because it would not be in the correct order. Again, folks, P corresponds with G. Angle P corresponds with angle G. So again, folks, you couldn't write it. You couldn't write this in the order of FG. Not if it was already in. Not if the first one was written as PQ. Okay. So again, this right here would not be correct because again, P corresponds with G, and Q corresponds with F. All right. So again, that statement right there is not correct. That congruent statement is not correct because again, they don't have the corresponding vertices, the corresponding angles in the same order. So again, this congruent statement right here would not be correct. Just wanted you to see that, okay? All right. Again, we'll have examples where we'll write out congruent statements and things like that, because again, that's technically what we're going to be, or at least for the, I guess, part of what we'll be discussing here in this lesson. All right. So again, folks, when you are naming congruent polygons, you need to write out. You need to make sure that you write out your congruent statement so that the corresponding vertices, or in other words, those corner points, those corresponding angles are written in the same order. I can't stress it enough. How many times have I said the same thing? I don't know, but I know that I'm emphasizing it. I don't know if your ears, I don't know if it's falling on deaf ears. I really hope not. But again, you can't say to Mr. Starkey, isn't stressing it, emphasizing it. Okay, I'm talking to my students enrolled in my classes. Anyway, all right, moving on. Yeah, I had to erase all of that. All right, so again, folks, we're gonna move on. All right, so again, folks, we're going to move on, but again, you can see here that all of the corresponding parts for these two polygons, for those two polygons, are congruent. And again, you can tell that based on those congruency marks. They all of the parts have matching congruency symbols, and so we know that they are congruent because all of the parts, all the corresponding parts are congruent. And therefore, guys, again, you can write out the whole congruent statement there, that polygon PQRS is congruent to polygon GFED. And it has to be in that order. So, guys, let me just show you real quick, just to emphasize what I was saying about listing those corresponding vertices in the correct order. Folks, if we decided to switch the order of those vertices, then another way that we can write we could write that same congruent statement for those two polygons. Now, I want to make it crystal clear for you that if we decided to switch the order of those vertices for one of the polygons, so like if we wanted to switch the order and we wanted to say polygon RP SQ, right? So if we wanted to call that polygon RPSQ, you get what I'm saying? So if we wanted to call that polygon RPSQ, and we wanted to write a congruent statement with the other polygon, guess what? We would have to reorder. We would have to reorder those other vertices so that they matched up. So, folks, since R is coming first, guess what? Which vertice or which vertex matches or corresponds with the vertex R? You can tell that based on the congruent statement that we have for our angle. Or either that, or you can literally look at the diagram and tell that the corresponding angle with angle R is angle E, right? Because they have matching congruency symbols for those two angles. So since R comes first, guess what? We got to put E first if we were going to reorder it. Y'all get what I'm saying? Because R and E are corresponding vertexes. So if you're going to put R first, you have to put E first in the other one. Y'all get what I'm saying? Then next, folks, if you were going to put P next, okay, well, the one that goes with P is G, right? So, again, folks, if P was going to be the second one, then you'd have to put G next. Y'all get what I'm saying? I mean, do y'all really get what I'm saying? If you switch the order of the vertex when you're doing your congruency statement, then you're going to have to make sure that the order for the other one is switched as well. So the order that you write this in, it matters. Okay? You need to make sure that you do it like I'm telling you to do it, and that you make sure that your corresponding vertexes, your corresponding vertices are in the same order. I'm trying to make sure that you get what I'm saying before we even look at an example. Okay? Because I don't want nobody to be confused even by what I'm saying. Okay? So, again, if S was coming next, okay, well, S is corresponding with D, right? S is corresponding with D. So if S came next, then D would have to be the next one, right? Make sure that they're in the right order. And then, of course, guys, if Q was the last one that was written, okay, what shape can I do for a Q? Okay, we did a little oval shape here, triangle there. I want to see if it'll do this right here. It probably ain't going to do nothing special. Oh, snap! Oh, snap! Okay. 1, 2, 3, 4, 5, 6, hexagon. A hexagon. I really am kind of surprised that it did that. It's kind of a pleasant surprise, I guess. But it did it, nonetheless. Hexagon. Look at there. All right. It did it, too. All right, so again, folks, if Q is the last one that was written in that order, then F would have to be the last one that goes there. So again, folks, before we even looked at an example, I've taken a few minutes just trying to make sure that you get what I'm saying with this thing here, okay? About your corresponding vertices needing to be in the same order. And again, we are going to look at separate examples that kind of show that as well, and more. But yeah, alrighty. So now we're going to go ahead on and move on, okay? Okay, so folks, next we are going to look at a few properties that are commonly used, or a few properties of congruence that you will see again as we go a little bit further and deeper into this whole congruence thing. I know a lot of you might be thinking, "Oh, Mr. Target, I know everything I need to know about congruence." That's completely not true. Trust me when I tell you. Unless you've already taken this course, yeah, and whatever the following courses that you're going to be taking, my students who are enrolled in my class, trust me, you don't know everything that there is to know. I don't even know everything that there is to know, and I'm a math teacher. Okay, there's a lot of stuff I can learn about math. So when I tell you that you don't know everything about congruence, just take my word for it. Anyway, so next we're going to look at a few properties of congruence, and these properties of congruence are can also be properties of equality as well. And again, we know that congruence is sort of related to equality, seeing as to how things are congruent if they have the equal measures, right? Equal measures, equality, right? So we know that congruence and equality can be kind of related to each other. But again, we're going to look at a few properties here. The reflexive property, the symmetric property, and the transitive property. Not only just that, but and we may mention also the substitution property, but we'll see about that one. Okay, so folks, here I've got these different photos here, these different pictures to the left are illustrating the reflexive property, the symmetric property, and the transitive property of equality. Now, folks, when it says that they're illustrating, these photos are illustrating, that means that these are just illustrations that are just kind of used to help you see and visualize what these properties are representing. But again, folks, so let me explain what's going on with each of these properties and each of these illustrations that you see here. All right, so folks, and I'll try to probably see if I can erase what I'm writing right now, but anyway, just so you get what's going on here. The reflexive property, this is an illustration of the reflexive property. It says here that Gene is the same height as Gene, right? So here it's talking about, it's comparing Gene's height to itself. So it takes a value or geometric figure, the reflexive property, takes either some type of value or geometric figure. Yeah, okay, that must not be where I need to write that then, huh? It takes a value or geometric figure, and it either sets that value equal to itself, right? So it either sets the value equal to itself, or it takes that geometric figure and sets the geometric figure congruent to itself, right? So with the reflexive property, think of it sort of like a reflection, like you're looking in a mirror. Well, what do you see when you look in a mirror? You see yourself, right? Reflexive property. All right, so the reflexive property compares some type of value to itself, and if it's comparing a value to itself, then it's the reflexive property of equality, or it compares some type of geometric figure to itself, meaning that it's going to be saying that some type of geometric figure is congruent to itself. And if it's comparing some geometric figure to itself, then it's going to be the reflexive property of congruence. So again, folks, with the reflexive property, that is something that compares a value or a geometric figure to itself, and it pretty much where you can write out some type of expression about that the value is equal to itself, or the geometric figure is congruent to itself. If you all get what I'm saying, right? So all three of these properties, the reflexive property, symmetric property, and transitive property, it can be used in statements about equality, or they can be used in statements about congruence, which is what I literally just said. That again, that if you got a value that's being compared to itself, you can write that value is equal to itself, and if you have some geometric figure that is being compared to itself, you can write that geometric figure is congruent to itself. And again, folks, I'm going to show you like these algebraic expressions like that are written out using these reflexive properties. But first, let me just kind of show you this illustration, okay, to help kind of explain, explain. Now, again, folks, these are just illustrations to help sort of kind of explain what these properties are about and what they're comparing and how, yeah, and things like that. Yeah, I didn't mean to erase that part of that, did I? Oh, I just didn't want that to look so weird. Come on. There we go. All right. Yeah, that still looks weird, but it's all goods. Itself. Okay, at least we can somewhat tell now that we're writing. Yeah, not really. Still don't quite look all that great, huh? Let me separate them letters a little bit more. That was bothering me. It might not have been bothering y'all. It was bothering me, the way that looked. I like to actually write so that my stuff looks legible, where not only y'all can read it, but I need to be able to read it myself too. Okay. All right, so that's the reflexive property. The symmetric property is comparing two different values, and with the symmetric property, so as you can see, based on this illustration here, it says if Gene is the same height as Pedro, so if Gene and Pedro are the same height, then what must be true is that Pedro must be the same height as Gene. So you see what happened there? Did you see what happened? Did you saw it? So the first one said if Gene and Pedro are the same height, and then the second one said then Pedro is the same height as Gene. You see what I'm saying? You see what I'm saying? Y'all see that? Did y'all see what they did? Did y'all see what they did? Where they switched the order? Where they have switched the order of the equality, or they may switch the order of the congruence. Again, it could be a statement. It could be a congruent statement, or it can be some type of equality statement. And we know an equality statement is, of course, guys, an equation. Duh. But anyway, so again, it could switch the order of your equality. So like if two values are the same, like Gene's height and Pedro's height, then you could switch the order of that equality. If it was two values that are the same, like two people's height that are the same, like what's illustrated here. So again, if it was two values that were the same and it was equal to each other, then you could switch the order of that equality. And then, guys, if you had two congruent figures, then and you had some type of congruent statement that said that this figure is congruent to that figure, then you could switch the order of that congruent statement, and then it would say that figure is congruent to this figure, and instead of having it in the same order, it would be switched order. You get what I'm saying? And again, folks, I'm going to show you how the symmetric property looks when you have an algebraic expression written. But again, folks, this is just an illustration, just to kind of show you what's up. So again, with the reflexive property, it compares some value to itself, or some geometric figure to itself. With the symmetric property, it compares two different values or two different geometric figures. And again, you could switch the order of your equality if you're talking about two values, or you could switch the order of your congruence if you're talking about two geometric figures that are congruent to each other. But anyway, that's the reflexive property and the symmetric property. And then, folks, with the transitive property, and again, folks, I just want to explain what these properties are about before I show you the algebraic expressions for them. And we want to explain that using these illustrations. Okay? With Gene's height and Pedro's height, and even with Chris's height. Pedro, Gene, and Chris. Yeah. All right, so anyway, with the transitive property, so you see out here, it's comparing at least three different things. It can compare at least three values, or it could compare at least three geometric figures. Of course, guys, as I've mentioned before, if it's comparing three values, then it would be equality. And it would be, that those values are equal to each other. Like these three guys' is height here. Height is a value, is a type of value, and so this would be properties of equality that's being illustrated here, because it's talking about a particular value, the same height here that's being compared. All right. So again, folks, here it says if Gene is the same height as Pedro, and if Pedro is the same height as Chris, then what must be true is that Gene must be the same height as Chris. Now you see that? You see that? They compared Gene with Pedro. Cut right there. All right. Then they compared Pedro to Chris. You see that? And then because they compared, and let me just show you here, because again this is an illustration. So let me show you what's going on. Let me show you what's going on. right here. You see this fella right here? Y'all see Pedro? Look at Pedro. You see him? y'all see him. Y'all see Pedro? Look at Pedro. Look at Pedro. Pedro is who we call the middleman. I'm not saying that we got some type of transaction going on here and we just exchanging money from one man to a middleman, and the middleman is just gonna give money to the third man. I ain't talking like that, but again, I am sort of kind of talking like that. But again, you see, Pedro here is sort of like a little middleman. You see, Pedro is the one thing that connects Gene and Chris. You see what I'm saying? So Gene is the same height as Pedro, and also Chris is the same height as Pedro. Y'all get what I'm saying? Pedro is sort of like a little middleman. See, you see what I'm saying? Y'all see what I'm saying? You see? And so look at that. We're gonna go ahead and cut the middleman out. Yeah, that's pretty much what the transitive property does. The transitive property sort of kind of like cuts out that middleman. You know what I'm saying? So again, if Gene is the same height as Pedro and Pedro is the same height as Chris, guess what? We're gonna cut out that middleman. We're gonna cut out Pedro's height altogether, and we're gonna go ahead on and do a little logical jump here. And we're going to be able to say now that Gene's height has to be the same height as Chris's. Okay? And that should be logical to you. If both Gene and Pedro are 5 feet tall, and then also Pedro and Chris are both 5 feet tall, right? Then you can cut out that middleman of Pedro, and now we can say that Gene and Chris have to be the same height as each other. Y'all get what I'm saying? Y'all get what I'm saying? So with the transitive property, it's like you can cut out that middleman. All right, and this is just an illustration. These three photos, they're illustrating, and it's a way to kind of help explain sort of what these three properties are about. And it's not actually, like stating these three properties, but it's just an illustration. Okay. All right. So the transitive property sort of, and this is just sort of like what I'm writing here about this, like the whole itself thing, the whole switched order, and the whole cuts out the middleman. I'm writing here is just sort of like a little layman's terms thing that sort of help explain. What's going on. Like I said, that it cuts out the middleman. This is the way I remember these three properties. And hopefully it's a way that you will be able to help remember these three properties too. Okay? Cuts out the middleman. And of course, guys, we know that it does not literally have to be a person that we talking about. Y'all know what I'm talking about. If A equals C and C equals D, let me just show you with the transitive property. Let me just show you real quick, and then I'll show you these three properties written out in algebraic terms, like what I'm writing out right here. If A equals C and C equals F, right? Then you can literally cut out that middleman. With the transitive property, if that right there is true, if A equals C and C equals to F, then you can literally cut out that middleman. You can cut out the C altogether. Just completely forget about the C. Cut him out. Forget about him. He ain't even important. He don't even matter. He do, but he don't. Cut that middleman out. Cut him on out. Alright? Cut that middleman out. And what must be true is the fact that A must be equal to F. Alright? I mean, hey, that got to be true. Got to be true. Just got to be. I mean, if C was 5, right? So if both of these, if the value of C was actually 5, right? If A was equal to 5 and F was equal to 5, that means that A and F would have to be the same, length. I mean, it's just got to make sense, right? I mean, anyway, I ain't gonna take much longer here. I just wanted to explain and illustrate those three properties for you. We're gonna show you these three properties using algebraic expressions and equations and congruency statements. All right, so folks, here we've got shown like how it could be written using algebraic expressions, and of course that we're talking about where algebraic expressions are also written as part of equations and as part of congruent statements. So again, folks, as we mentioned before, those three properties, they're properties of equality, and they can also be properties of congruence as well. So again, folks, as we mentioned before, when we looked at that little illustration with those guys and their heights, as we mentioned before, the reflexive property is pretty much focusing on some type of value or some type of figure and comparing it to itself. So again, as you can see here, they've got written here the length of segment AB is equal to the length of segment AB, and then they've got the measure of angle A is equal to the measure of angle A. So again, folks, as a part of what the reflexive property is pretty much saying is that any value is equal to itself, right? Okay, and then they've got the same sort of kind of situation set up with these congruent statements. They've got here that segment AB is congruent to segment AB. So it's congruent to itself. The segment itself, the geometric figure, is congruent to itself, right? And then they've got angle A is congruent to itself. So again, what that's saying, if we use the reflexive property as a congruence property, then what it's saying is any geometric figure is congruent to itself. So that's the reflexive property, and again, it can be used as a property of equality if it's setting the same value equal to itself, or it can be used as a property of congruence if it is saying that a geometric figure is congruent to itself. Symmetric property, again, folks, it can either be a property of equality or a property of congruence. You can see the equations that are written there with the algebraic expressions, and you can see the congruent statements that are written there with the algebraic expressions. But again, folks, what the symmetric property of equality is saying is that the order of two values in an equation can be switched, like what you see here. If the length of segment AB is equal to segment CD, or is equal to the length of segment CD, then literally you can switch the order of those two, right? You can switch the order of those two lengths in that equation, and now you can say that because the first part was true, now you can switch the order of it, and you can say that, okay, the length of segment CD is equal to the length of segment AB. All right, you should see that clearly. All right, so it works like that as a property of equality, and then it works also as a property of congruence, where the order can be switched with two congruent figures in a congruent statement. So like what you see there, with angle A is congruent to angle B. If angle A is congruent to angle B, what that means is that if you switch the order of that congruent statement, that means that also angle B must be congruent to angle A. Okay. All right, and then the last one, the transitive property here. It can be used as an equality, a property of equality, or it can be used as a property of congruence. So again, as a property of equality, what the transitive property pretty much says is that when two values are both equal to a third value, okay, and again, when we did the little illustration a few minutes ago, we called that third value, or in layman's terms, we call that third value the middleman, and we said you could cut out the middleman, you could get rid of the middleman. All right, so again, when two values are both equal to a third value, then those two values must be equal to each other. Okay, and that's what you see here, written out with these equations. If the length of segment AB is equal to the length of segment CD, and CD is equal to EF, then so again, both of those two segments are equal to the length of segment CD, and you can see that. So that third value over here would be the length of segment CD. Okay, and so since both of those values are equal to that same value, the length of segment CD, that means that those two values are equal to each other. The length of AB and the length of segment EF have to be equal to each other. All right, but anyway, that's how that works, guys. And then, of course, it can be used as a congruence property. And as a congruence property, what the transitive property states is when two geometric figures are both congruent to a third figure, then those two figures must be congruent to each other. Okay, so hopefully that makes sense. Okay, yeah. That's as much as I can do to explain it. That the reflexive property compares something to itself. The symmetric property switches the order, says that you can switch the order of equality, or you can switch the order of in a congruent statement like that. And the transitive property pretty much, and I'm saying it right now in layman's terms, but again, says pretty much that you can cut out the third man. Now, again, folks, if you are my student enrolled in my classes and you're doing and you're answering my discussion questions, what I have written out here in the red with these red words is what you need to be looking at. I'm not asking you to give me layman's terms or anything like that. I'm asking you to state something specific that I've said here, that I have written here, that you can't get mixed up with anything else. Because not only have I said it, I've written it as well. If it's said and written, you can't refute that. Not with me. You sure can't. All right, anyway, all right, those are those three properties. Okay, so next, guys, we're just going to look at a few little examples of just to show you and to further explain what's all in this lesson and what you'll be expected to kind of know and be able to do with the practice that's involved with this particular lesson. We're going to show you a few examples coming right up. All right, so here we go, folks. Here's example one. So it says, for the two congruent polygons, and you see them right here. You see those two triangles. So it is telling you that these two triangles are congruent. It says, do the following things. It says, use congruent statements to list the corresponding parts. And then it says also, complete the following congruent statements. Haha. So let's do the first thing, and then let's do the second thing. Let's do this. I said, let's do this. All right, so number one, what they ask you not to do. Excuse me. All right, so they said use congruent statements to list the corresponding parts. All right, so if we were going to list out the corresponding, give me a second here. If we were going to list out the corresponding angles, do that. And then, of course, if we were going to list out the corresponding sides, let's do that too. Well, we list out all of those things right there. Okay, so let's go ahead on and list out those corresponding angles. All right, so let's see here. If we just pick a random angle, right? Angle, I don't know, E, right? Which angle in the other triangle matches angle E? All right. So, excuse me. Even though they don't have any congruence marks, when they don't have anything like that, and they tell you that two polygons are congruent, this is the one time that you can assume, and of course, guys, use common sense. This is the one time that you can assume, even though they don't have the congruence marks, because and technically you're not assuming because they literally tell you that these two polygons are congruent. All right, so but again, guys, the angle that looks the most like angle E is clearly angle B. All right, so the angle from the other triangle that looks the most like angle E is angle B. Okay. All right, so that would be the corresponding angle for angle E. Would be angle B there. All right, and then if we pick another one, let's choose F. Sure, why not? Okay. Angle F is congruent to which angle? All right, so when we look at angle F, which angle in the other triangle looks the most like angle F? Well, I'm going to have to go with angle C. Yeah, I'm going to have to go with angle C right there. Yes, I'm is. Oh, yes, I'm is. Yeah. Just pretend like I'm using proper English. All right. So angle F. Oops. Why y'all let me do that? Angle F is congruent to angle C. Angle E is congruent to angle B. And of course, angle D is congruent to angle A. So folks, these two polygons are congruent. It looks like there's been some kind of rotation, some type of rotation of some kind. If we were going to talk about what type of rigid motion or what type of isometry, what type of transformation could have created these two congruent polygons. It looks like some type of rotation has happened, like a rotation of 90 degrees counterclockwise around some type of point or another, or around some kind of axis. But anyway, and I'm going to erase what I just wrote there about that whole rotation. But again, folks, just to tie that in. All right, and then, folks, if we're going to list out our corresponding sides, again, if we're going to list out corresponding sides, let's just pick a random side, like side I don't know, side FE. Who knows? Side FE will be congruent to which side? Okay, so make sure that when you do this congruent statement that you use the corresponding parts, the corresponding angles, that you match them up, that you put them in the right order. Okay. All right. So, excuse me. Okay. Yeah. Sorry about that. The corresponding angle for angle F was angle C, right? So if you're going to put these, if you're going to put this in the right order, doing this congruent statement, then you're going to have to put C first, because C is the angle that corresponds with angle F. So since F came first right here for this segment, then you're going to have to put C first for this segment, because F and C are corresponding angles. And you want to make sure that the order lines up, that the order matches when you write out this congruent statement. F and C are both first when we write this out, okay? And then the angle that corresponds with angle E is angle B, right? So B needs to come last, the same way that E comes last. E is last, B needs to be last. Okay, that looks a little bit too much like an 8 for me. I'm going to have to erase that. And I'm the one that wrote it. And if it looked like an 8 to me and I'm the person that wrote it, I know it's got to look like an 8 to y'all. It's a little bit better. A little bit better. At least it don't look like an 8 anymore. Might not look like a B, but it don't look like an 8 no more. Alright. Alright, that's one corresponding side. Let's just do another random side. Let's just pick something like a rumma. BA. Okay. See if we can write that a little bit neater. All right, so segment BA, if we had to finish out this little congruent statement, segment BA is congruent to what? All right, and make sure that you put the corresponding parts to this in the right order. Which part corresponds with angle B? Well, angle E corresponds with angle B, right? So the E would have to come first when we do that. And then which part corresponds with angle A? Well, angle D corresponds with angle A. So E would have to come first and D would have to come last in order for the order to match up with the corresponding parts. B and E are corresponding, so they both come first. And then A and D are corresponding, so they come last, okay? It may seem like I'm over-explaining, but trust me, folks, I need to make sure that you get what I'm saying, and okay, about how you need to write out these congruent statements. So yeah, all righty. And then the last one, the last side is side BC, or side whatever. All right, we just gonna write it out over here. Side BC. Why not? Oops, sorry, we already used side BC. All right, because we had CB right there. Okay. What we got? Aha, there we go. FD. Side FD. All right, so the one that would be going with that, completing this congruency statement. Okay, F corresponds with C, so C would have to come first, and D corresponds with A, so A would have to come first. So, folks, we've written out, we've used congruent statements to list our corresponding parts, our corresponding angles, and our corresponding sides. In those two congruent triangles. And now, folks, we're gonna complete these congruency statements. I'm gonna go ahead on and fill them in based on what's already written up there. Yeah, we're gonna go ahead on and do that right here, right now, because I don't feel like writing that over again. All right, triangle DEF is congruent to, why y'all let me write equal for all of those instead of congruent? That's okay. Y'all know what I was trying to write. And if you don't know what I was trying to write, You know now. If you didn't know, now you know. Congruent statements. Wow. This is just so sloppy, but it's all good. Alright, so triangle DEF is congruent to triangle blankety blankety blank. Now, all of these statements technically say the same thing, that these two triangles are congruent to each other. But guys, the order that you got these particular letters in matters. The order that you got these vertices in, it matters. Okay, and if you switch the order of the vertices in one triangle, then you got to switch the order when you complete the congruent statement. So that's what I'm showing you here now, and I'm emphasizing it. I'm reiterating it, emphasizing it. Okay, so the part so for this first one with triangle DEF, okay, the part that goes with the vertex D is A, right? Give me a sec. I want to write that in green. All right, so A goes with D. The part that goes with E is B, and the part that goes with F is C, right? So if we complete this statement here, it would be triangle ABC. As completing this one. All right, if we complete this next one with triangle CAB, then the part that goes with C is F. The part that goes with A is D. And the part that goes with B is E. So if we had to complete this statement, triangle CAB is congruent to triangle FDE. All right, the next one, triangle CBA. If we had to complete that congruent statement, again, the part that goes with C is F. The part that goes with B is E. And the part that goes with A is D. So again, completing this congruent statement, it would say that triangle CBA is congruent to triangle FED. All right, and then this last congruent statement here, triangle EFD. It's congruent to triangle what? Okay, E. The part that goes with E is B. The part that goes with F is C, and the part that goes with D is A. All right. So completing this congruent statement, triangle EFD would be congruent to triangle BCA. Okay. All right. So that part right there. Okay. All right, folks. So here we go with example 2. In this one, they're saying for the two congruent polygons, do the following. So again, here they're letting you know again that these two polygons are congruent, and they want you to mark the corresponding angles with congruency marks. So actually like put congruency marks on those corresponding angles. Like, you know, if I was to put you know, like one little thingy there, if I was to put like two little thingies there, you get what I'm saying? I'm gonna try to make those a little bit smaller though, and you know, I was to put like three things there. Okay, so I'm just gonna make this one here the one that just has one, and this one here is gonna have 4 of them. And 1, 2, 3, 4. Boom. Alright. So now what I put right there isn't necessarily your isn't necessarily congruency marks because you don't see matching marks in the other diagram just yet. But that's what I'm talking about. So we'll put those matching marks in the other ones where the corresponding angles are marked using congruency marks for the angles. Okay, so y'all know what I'm talking about. Alrighty. So here, the next thing that they're asking you to do is to write in the actual side lengths for all of the sides. Yes. So they do not want you to put congruency marks for the sides. So they don't want you to do what I'm doing right now. They don't want you to put congruency marks for the side lengths. So what I'm putting on the side lengths right now, they do not want you to do that. That's not what they're asking you to do, okay? So I'm erasing that. That is not what they're asking you to do. They're not asking you to use congruency marks. They're asking you to put the actual side length for all the sides, okay? So just get that clear, all right? Not to say that you can't read, but just want to make sure you know what they ask you to do, okay? All right. And then where it says, finish this congruent statement. Trapezoid BDAC is congruent to trapezoid blankety blankety blank blank blank, whatever, right? All right, so folks, and again, we haven't talked about this in this particular class, but I'm sure that at some point in time in your life, I'm pretty sure that it can't be the first time that you've heard the word trapezoid. But if it is, a trapezoid is a type of quadrilateral, a type of four-sided figure. Yeah, I'm writing that all sloppy, but it's all good. A four-sided figure. Four-sided polygon, anyway. So it's a quadrilateral that has where only two of its sides are parallel, where two of its opposite sides are parallel. Just in case somebody was wondering, okay, well, what in the world is a trapezoid? Yeah, okay, I got you covered. Where two of its opposite sides are parallel. That right there is what a trapezoid is, if anybody was wondering. All right, and let me just show you. In this trapezoid that I'm putting this green segment, that side and this opposite side to that one, these two opposite sides are parallel. How do I know they're parallel? They're both horizontal. And then horizontal lines, two horizontal lines are parallel because two horizontal lines have the same slope. And horizontal lines have a slope of 0. Anyway, we can't go into all of that right now, but just take my word for it that these are trapezoids. Anyway, where you got, it's a quadrilateral with two of its opposite sides are parallel. I'm erasing all of that. Empty waste. All right, so, oops, I didn't mean to erase that. All right, hold on. And they still erased it, didn't they? There we go. Alrighty, so let's go ahead on and do this one here. First come first, let's go ahead on and mark our corresponding angles. Wow, what is that? Alright, so let's mark the rest of our corresponding angles using those congruency marks. Which angle would you guys say is going with angle E? With angle E. Man, this is too tough. Oh my goodness. With angle E, oh my. Well, first off, angle E looks like it's a right angle. And I only see two other right angles in this other diagram. I only see two other right angles that it could be. So which one of those two looks like it could be corresponding with angle E? Right? There's your question, and there's your answer. Angle A is clearly the one that is corresponding with angle E. All right, there we'll put a little matching, corresponding congruency marks. Which angle is corresponding with angle H? Okay, well, clearly, angle D is the one that's corresponding with angle H. And we'll put the little matching congruency mark in there with. All right, what about angle G? Which one of the angles in the other triangle is corresponding with angle G? Well, look-alike to me, really look-alike to me, that would have to be angle C. An acute angle. It look like angle G and angle C are the only two acute angles there. And then which angle is corresponding with angle F? Well, look-alike to me, the only one that's left that could be corresponding with angle F is clearly angle B. Oops, well, that's just a sloppy. It'll be all right. It'll be all right. Okay, so we got our congruent or our corresponding angles marked with congruency marks. All right, we're gonna go ahead on and do part 3 right now, and then we're gonna do part 2 of this after we do. So let's finish this congruent statement. Trapezoid BDAC would be congruent to trapezoid what? All right, so since we just now marked our congruent or our corresponding angles, right? Then which angle goes with angle B, right? Because we got to put them in a certain order, right? In the same order. The corresponding angles in this congruent statement have to be written in the same order. So which angle corresponds with angle B? Well, we just marked it. Angle F corresponds with angle B. Which angle corresponds with angle D? We just marked it. Angle H corresponds with D. Which one corresponds with A? We marked it. Angle E corresponds with A. And then which one corresponds with? Wow, that's just completely, it's too sloppy. I'm sorry, I got to erase that. Might not even been bothering y'all, but it was bothering me. Still don't look too much better, but it'll be all right. All right, and then which one is corresponding with C? Well, we marked it. G, angle G is corresponding with C. All right, so that completes that congruent statement for part 3. All right, now guys, if we're going to do part 2, for most of these sides are vertical and horizontal. So for these ones that are vertical and horizontal, all you got to do is just count it. Literally, just count. Just count. You know how to count, don't you? All right, I know you do. I'm not going to antagonize you. All right, so if we just count the spaces there, count how many units that is, right? For this vertical side right here, side AB, if we count that, that's 1, 2, 3, 4, right? Oops, see? They know I wasn't trying to zoom out like that, but it's all good. It's all's good in the neighborhood. All's good. All righty. So again, folks, if you just count that, literally, just count it. All right, so if you just count that, that's 4 right here. And of course, guys, its congruent or corresponding side would have the same exact length, right? 4 and 4, all right? And if we look at this horizontal side, side BC here, If we just count that as 1, 2, 3, 4, 5, let's count that again. 1, 2, 3, 4, 5. Count Dracula. All right, I enjoyed that entirely too much. Okay, so we know that one has 5 units, and this one has a length of 5 units as well. Those corresponding parts. We're writing in the actual side lengths. All right, that was one of the horizontal sides, the longer horizontal side. The shorter horizontal side clearly only has a length of 1 unit, right? And let me just write that so that looks like a 1 as well. So nobody think that that's something that it ain't. All right, so that one has a length of 1. And here goes my favorite part, y'all. Yeah. You know I had to do my little devious laugh there. Here goes my favorite part, y'all. Guess what? We talked about finding the length, finding the distance and the length, right? When we did the distance formula and the Pythagorean theorem. And we talked about how the Pythagorean theorem and the distance formula were related, right? So guess what, y'all? The distance right here of this segment. We looked at, all right, yeah, hold on one sec, y'all. Hold on one sec, because I don't want that to look too sloppy. I'm gonna have to pull out my ruler. Give me a sec here. I'm gonna have to pull out my ruler. Yes, Oh, yes, I am. Okay, so you guys see there that side length right there that I got marked. Guess what? We talked about this before. We talked about how to find the distance and the length. We talked about in both when we talked about the Pythagorean theorem and finding the distance in the coordinate plane using the distance formula. Now here, guys, we're not going to use the distance formula because we don't have a x-axis and a y-axis on this particular grid and coordinate plane. So for this one, we're gonna use what we got here. We're gonna use our vertical length and our horizontal length. And the fact that this vertical length and horizontal length form a right triangle, right? That's what we's gonna do, ain't it? Ain't that what we gonna do? I hope that's what y'all was gonna say we were gonna do, right? It makes sense to me. Do it make sense to y'all? Is this too much? No, it's not too much, right? It's just reiterating something that we've already talked about, correct? Right, then it shouldn't be an issue then. Because we know that horizontal length and that vertical length, they form a right triangle. The two legs right there, the two legs of that right triangle, this vertical length is one of the legs of the right triangle, and this horizontal length is one of the legs of this right triangle, right? So we got our two legs, and we should know really what those two lengths are already, since we kind of already marked them anyway. Or even if we haven't marked them yet, it's so easy to figure out what those two lengths are, the vertical one and the horizontal one, right? Because this is definitely a right triangle that we can find our distance here, and we can find the distance that we're looking for, and we're looking for our hypotenuse here. And we don't know our hypotenuse. So we've got our leg, we got both our leg lengths, and we don't know what our hypotenuse is. All right, so folks, both of the leg lengths, like I said, if you just count those, that's 4 right there. Okay, I'm not gonna put that up there with the little graph paper. I'm gonna put that down here, and then the horizontal distance is the same thing, 4. All right, so guess what, folks? Since we got ourselves a right triangle, because we know that's what happens when you got a vertical line that intersects with the horizontal line. Yeah, they form a right angle. Yeah, it definitely does. So we got ourselves a right triangle here, and so we need to go ahead on and use. Do you guys remember what this theorem is called that we need to use to find this third side in this triangle, in this right triangle? You remember what this theorem is called? Since we got a right triangle, we need to use which theorem? What is it called again? I'm so glad y'all said the right thing. We need to use the Pythagorean theorem, y'all. Ain't that right? Ain't that right? Ain't that right? Let's use us some Pythagorean theorem. And let's find this third side of this right triangle. This missing side length of this right triangle. Oops. Well, I started off real neat. It didn't want to, my hand didn't want to cooperate. That's fine. All right, so let's use our Pythagorean theorem, which we know says that a squared plus b squared equals c squared. And we know the c always represents your hypotenuse, right? And for the other two legs can be a or b, but c is always your hypotenuse, correct? Yes, right? Awesome, lovely. I'm glad you know that. Alrighty. And then, so that means that if we plug in our parts here, 4 squared plus 4 squared for our two legs, A and B, and then all we got to do is finish solving for C. Isn't this awesome, y'all? We get to put in more than one concept here. That's so awesome because they'll do that on your final exam for like state given tests. Yeah, isn't that awesome? Lovely. All right, and you'll be able to say, man, I saw stuff like this one in Mr. Starkey's class. Awesome. Lovely. You won't be surprised. All right, so there, 4 squared is 16, and 16 plus 16 gives us 32. 32 equals c squared, and we should remember how to finish solving for this. The only way for us to get c all the way by itself is to get the squared to cancel out. So the inverse of a square is a square root, right? So you should remember that we have to take the square root on both sides of the equation here. And again, when we take the square root of a square, those two cancel each other out, the square root and the square, because they're inverse operations. So again, folks, if we were going to write out the exact length, we would write it out as the square root of 32. The exact length there is the square root of 32, and if we were going to write out this in its simplest radical form, if we were going to write it in its simplest radical form, oops, I don't know why I wrote that like that. It's all good. There we go. If we were going to write it in its simplest radical form, we would split it up into parts where one of those factors is a perfect square, right? So, yeah, we doing a little mini review here. We sure are. Yes, we are indeed. Yeah, you got to take those moments to do them. Yeah, so if we were going to write it in simplest radical form, that would be 4 times the square root of 2. All right, so the exact value would be the square root of 32, right? square root of 32 as the exact value. And again, if we were going to write it as in its simplest radical form, that would be 4 times the square root of 2, which, and again, we know that they're the exact same thing, the same value. And if we were gonna approximate and round off what that is, the square root of 32, not that I know exactly what the square root of 32 is, but I know that it's somewhere that is something in between 5 and 6. I know that for sure, that it's 5 point something. I might not know exactly what it is. If we were going to write out a rounded version of it, it would be 5 point something. Maybe I can guess right now. And if y'all got calculators, y'all can tell exactly what it would be. But it would definitely be 5 point something, right? If we were going to round it to its nearest tenth, it would be 5 point something. Like 5.2, 5.3, 4, something, 5.5, something in between 5 and 6, right? And they would have the same approximate value if you decided to write the rounded version of it. The approximate answer would be 5 point something, right? Again, I don't have a calculator on me. And granted, I can do a lot of math in my head, but that one right there, I ain't trying to do. All right. So again, folks, we have answered this problem here. I think I'm going to show you just maybe possibly one or two more. Just depends. All right. So folks, here we go. Example 3. With this one, You're told that triangle ABC is congruent to triangle FDE. They give you this congruent statement, and in that congruent statement, folks, make sure that you pay attention to the corresponding parts. That again, angle A goes with angle B, angle A goes with angle F. Angle B goes with angle D. You get my drift, right? And angle C goes with angle E. Y'all get what I'm saying here, right? So make sure you pay attention to the order that they've got to the order that is written in with the congruent statement, okay? All right, because that congruent statement tells us a whole lot. All righty. So folks, the first thing that we're asked to do is find the value of x and find the value of y. That's actually all that they're asking us to do. But the first thing that we can do, for show, is we can go ahead on and find the third side here in this triangle. And so we know, guys, based on the triangle angle sum theorem, that all three of the angles in this triangle are supposed to add to 180 degrees. Triangle angle sum theorem. Wow, that is just sloppy, y'all. Only y'all can tell what it say. I'm alright with that. The triangle angle sum theorem says that all three of these angles here are supposed to add to 180 degrees. So if we want to find out what that missing angle is there, then we go ahead on and we do that. All right, so we got 108 degrees plus 48 degrees plus that missing angle there in this triangle on the left side, and all three of these interior angles are supposed to add to 180 degrees. So 108 plus 48 gives us 156. Oops, yeah, that's just a sloppy, but guess what? If you could tell what it say, I'm all right with that. 156 plus this missing third angle equals 180 degrees. Subtract 156, guys, and this missing angle here has to be 24. All right, so that means that this angle right here is 24 degrees. So now we know all three angles in this triangle on the left side. And so, folks, if this triangle on the left side is congruent to the triangle on the right side, that means that all of the angles or all of the corresponding angles over here are congruent to the corresponding angles there, right? So angle C is corresponding with angle E, right? So that means that angle E is clearly 108, right? Right? Those corresponding angles. Corresponding angles are congruent, or the corresponding parts of congruent triangles are congruent to each other. Are congruent. The corresponding angles have the same measure, right? So that means this one has to be 108. Okay, this one for angle B is corresponding with angle D, right? And so we know that angle D has to be the same as angle B. And so that means that Y has to be 48 degrees. And I apologize about how sloppy that looked. All right, let me try that again. That means that Y has to be 48 degrees. All right, if it's got to match up, if the corresponding angles have to be congruent with each other, that means that this angle here, angle A and angle F, correspond with each other. So if angle A is 24 degrees, that means the angle F has to be 24 degrees. Y'all see how we using everything that we've learned? I mean, even though this lesson here is technically not about the triangle angle sum theorem, we still have to use it. It's important. That's why we got to know all of this stuff. Okay? All right, but anyway, again, folks, we've got that this has to be 24 degrees. So, guys, now that we know what Y actually is, let's go ahead on and substitute. Now that we know the Y is 48, right? Y is actually 48. So let's substitute that value there in the place of Y. Okay, because we know the Y is 48. Wow, yeah, I ain't going to fit 48 there. Let's try that again. Y is 48, so that's 2x minus 48 equals 24. Right? If we substitute that value of Y, and y'all see that, right? That's what we just now did. We substituted that value of Y. All right. So now, guys, since we substituted this right here, all we need to do right now is solve this equation. The 2x minus 48 equals 24. Let's solve that equation, and then we'll have our answer for what Y equals. We'll have our answer for what X equals. We already know that Y equals 48, and now all we got to do is solve this equation and figure out what X equals. All right, so that equation, we're about to solve that. The 2x minus 48 equals 24. And then, folks, I'm going to show you this last example real quick. If we add 48 to both sides, we end up getting that 2x equals 72. And then if we divide by 2, we get that x equals 36. All right, so now we've got both of these angle measurements. Y equals 48 and x equals 36. Alrighty. Last example coming right up. Alright. So here we got example 4, folks. In this one, they tell us the triangle ABC. Wait a minute. Y'all, they ain't give us no diagram. What in the world are we supposed to do if they ain't give us no diagram? Huh. Well, folks, this ain't our first rodeo show. We've gone over examples in previous lessons similar to this, where we were dealing with triangles and stuff. We've gone over similar examples where there were word problems and we had to draw out our own triangles. Okay, so what's the problem? Draw out the triangles. Quit playing games. All right, so triangle ABC, draw out triangle ABC. Don't act like you don't know how to draw a triangle. Draw it out. Come on, quit fooling around. Nobody got time to play games. Draw yourself out 2 triangles. Make them look just alike. If you just want to be difficult and you don't want to make yours look just alike, then make them look different. Whatever floats your boat, okay? Whatever. Anyway, draw yourself out 2 triangles and label them. Label one of them as triangle ABC and label the other one as triangle JKL. ABC, JKL. All right. And then what I suggest doing is after you've drawn out those 2 triangles and have labeled have labeled your vertices ABC, JKL, go ahead on and put your congruency marks, all of your congruency marks in those things. So put your congruency marks in there for the corresponding angles. Angle A corresponds with angle J, right? Angle B corresponds with angle K. BK Burger King. Hey. All right. Yeah, I'm hungry, y'all. Y'all have to excuse me. I ain't ate nothing all day except for like granola bars. No, seriously, I haven't eaten anything all day except for like granola bars. Yeah. Anyway, it's okay. Yeah. I ate yesterday. I'm gonna eat when I get home. It's all good. All right. Let me see. And then angle C is congruent with angle L. So again, here's what I suggest you do. I suggest you go ahead on and mark your diagram and put in those congruency marks for those sides for the angles, for the corresponding angles, and for the corresponding sides. Okay, so AB, that side corresponds with JK. AC corresponds with JL, and side BC corresponds with side KL. Alrighty, so now that we've got this thing drawn, folks, they tell us or they give us this other information about these 2 side lengths. So we know that we've got 2 congruent triangles, and we've drawn them as such. We've drawn them as 2 congruent triangles. Okay, why didn't y'all tell me that I didn't put the congruency mark up here for angle L being corresponding with angle C? That's all good. All right, so the other information that we're given is that the length for side AB is 2x plus 12. All right, so the length for that side is 2x plus 12. And then they tell us that the length for side JK is 4x minus 50. Well, guess what, y'all? Those two sides just so happen to be, those 2 sides right there just so happen to be congruent. So guess what? Since them 2 sides right there are congruent, you already know what that means, don't you? I know some of y'all know what that means already. Since these 2 sides are congruent, I know y'all know what that means. I know that y'all know what that means. What we gonna do? What we gonna do? What we gonna do? I say, what we gonna do? We gonna go ahead on since we know that those 2 are congruent. We're gonna use the definition of congruent. The fact that those two sides are congruent to each other. Okay, why didn't y'all tell me I was spelling definition wrong? It's all good. I fixed it. Since we know those 2 sides are congruent to each other, then we know that that the measurements for those 2 are equal, right? So since AB is congruent to side JK, then we know that the length of AB, the length of segment AB is equal to the length of segment JK, right? So that's what we know. And now we're going to go ahead on and substitute right there. All right, we're going to go ahead on and substitute what we need to substitute in right here. And then we're going to solve this puppy. Yes, we are. Oh, yes, we is. And then I got to go. Because it's almost that time. And I ain't trying to get stuck here. And we don't want to get caught with this alarm going off. So, yeah. All right, so let's go ahead on and let's substitute what we got here. And what I mean by that, of course, is, yeah, since we got this statement right here of AB being equal to JK, well, guess what? They told us what AB was, or they told us what the length of AB was, right? Yeah, okay, I thought that was going to do that a little bit neater than that. Let's try this. Hey, all right. So they told us what AB was. Let's go ahead and plug that in. And they told us technically what JK was. So let's plug that in too. All right. Let's not act brand new. All right. So AB is equal to JK. That means that 2x plus 12 is equal to 4x minus 50. All right, folks, I'm not going to take up video time solving that. We're just going to show the answer for it, and then I got to get up out of here. All right, so folks, x equals 31. Again, when we solve out this equation that we got there, x equals 31. And folks, that's not it, because they asked us to find x, and they asked us to find AB, the length of AB. So guess what? We're going to have to substitute again. Substitute in our value for x and plug that into this other thing, into the statement for AB, into the equation that tells us what the length of AB is. So substitute yet again. All right. Since we know that AB is equal to 2x plus 12, go ahead on and plug in our value of x right there. Since our value of x is 31, that's 2 times 31 plus 12. 2 times 31 is 62, and 62 plus 12 gives us 74. Excuse me. Talking too fast, but it's all good because I need to be talking fast. That's 62 plus 12, which is 74. All right, so the length of AB is 74, folks. Okay, yeah, they ain't going to let me write that. All right, I got to go. We got to stop this video right now. I got to go. All right, that's it, folks. I hope that this has been helpful to you about congruence and triangle congruence and polygons, congruent polygons. I hope that this has been helpful to you. It's had a lot of information in here and some pretty decent examples too, if I might say so myself. I got to go. I do hope that it's been helpful. Good night. Bye-bye. See you later. Arrivederci. Adios. Au revoir. Bye.